exploring exoplanets, they probably think we're out there visiting them. That's totally out of the question. All we can do is try, we're stuck here on the Earth. All we can do is use telescopes and cameras and our ingenuity to try to figure out whether planets do exist around nearby stars. So it's kind of amazing that there are 5 or 6 different ways that all work pretty well.
So we're going to get to your book, Josh, but we're going to start with the rare Earth hypothesis, which is something I've always wanted to ask someone of your incredible intellect and breadth of knowledge. And that's that the conditions that allow complex life on Earth are so specific that intelligent life, certainly, maybe life at all, is very likely uncommon in the universe. And I wonder how you would react to this statement. If you got a letter from God or Mother Nature and it said, life is only existent on Earth, everything else is barren, cold, and lifeless, would you still say there's a point to studying exoplanets?
I think so. I think that the search for life is definitely one of the field's great kind of animating principles. And that's true of the public, and it's also true of scientists. It's a thrill to be able to be part of this very long-term quest. And I remain interested in that question. I don't happen to work on it personally. I am not really on a day-to-day basis trying to find life on other planets. Mostly about trying to find the planets and study their properties. And there are a bunch of reasons to do it that have nothing to do with life. One of them is just generally exploratory. What is out there? We all learn in elementary school about the properties of the planets and the solar system, and each one has its own story. Saturn has rings, and Uranus is tipped on its side. So what are the other planetary systems like? What kind of surprising features do they have? Do the planets resemble the ones in our solar system or not? And the field has been very good to us in providing lots of surprises and lots of planets that do not resemble any of our friends in the solar system. So there's an exploratory purpose, and then there's a more kind of scientific purpose, which is to try and figure out where planets come from. If we didn't already know planets existed, if we just knew the laws of physics and we were told, okay, you're in a galaxy, there's clouds of hydrogen and helium, there's a little bit of heavier elements sprinkled around, what happens next? I'm not sure. It would take a long time before anybody would venture to predict that planets would exist. They're the outcome of a really complicated, really interesting set of processes that we only dimly understand. So a lot of the here and now in this field is not about trying to find extraterrestrial life, but it's trying to explore the properties of other planetary systems and figure out where planets come from.
I want to talk about the only planet we know has life, which is the Earth. And you talk towards the end of the book about Carl Sagan and when he and other collaborators turned the Galileo spacecraft in on itself. He liked to do that. I think he did the Voyager spacecraft and it came to the pale blue dot, as you know about. And you mentioned in the book the kind of signs of life. There's 2 of them in particular that you mentioned, but I want to highlight a third one when we get to it. Gases in the Earth's atmosphere detectable through spectroscopy are indicative of life, and liquid water, while not directly a proof of life, is the indicator of strong potential habitability. Why are we so obsessed with with Earth-like planets in terms of what could be out there? Surely, as they say in Star Trek, it could be life, but not as we know it. So how is it possible to really make any conclusions from a sample size of 1 that would guide you in your research? How do you handle such endeavors?
Yeah, it is a very good question. And there is this concept that we talk about all the time, the habitable zone of a star. The range of distances from the star where an Earth-like planet would have just the right temperature to have liquid water. I don't know how seriously to take that concept. It sounds like maybe you don't either. We don't have a theory that tells us how life got started here. So we do not know what was required here. And likewise, we don't know even if there is an identical planet somewhere else, whether that would be enough to guarantee the formation of life elsewhere. So because we don't know either of those things, all we can do is guess based on what we do know for sure, which is that life exists here on the Earth. So I think about it not as a kind of scientific advance to say that we're going to explore the habitable zone, but more as a prioritization of resources. If we have limited time and limited resources and we want to look for life elsewhere, which planets deserve the most emphasis? Which ones should we build our telescopes specifically to study? Maybe those should be the ones that resemble the Earth in what we think are the key respects. I wouldn't go any further than that. I don't know how much we're increasing the odds of success by doing that, but it does seem logical to follow that path while also being open-minded enough to the possibility of surprise.
What's the role of a star on an exoplanet? You talk about the various types of arrangements, I'd say family dynamics maybe with stars, and in fact I want to cover the planet exoplanet, probably the first one, right? That was discovered around a pulsar. Is that not correct? So what is the relationship of the host star to the exoplanet and its potential habitability?
Yeah, so the first thing to know is that most of our knowledge is about stars that resemble the sun. And that's for mainly technological reasons. Detecting planets is very difficult. We can get into why it's so difficult. And so we have to use very high technology. We have to make very precise measurements. And naturally, all of our optics, all of our telescopes are geared towards visible light. And stars like the sun are the ones that put out most of their energy in visible light. So I can tell you a lot about the planets that exist around stars that are, say, between half the mass of the sun and maybe 1.5 times the mass of the sun. But that's a pretty narrow range. There's all kinds of other stars. There's a lot of excitement about trying to find planets around really tiny stars, maybe 1/10 of the mass of the sun, because they're very common and they're very convenient in a lot of ways. And there's also a lot of interest, although not much activity, in trying to find planets around stars much more massive than the sun, stars that will eventually become supernovae, that will explode someday. And then, as you said, there's also been some surprises about the types of stars where you never would think you'd find an exoplanet, but you actually do find at least a few systems. One of them was the pulsar, a neutron star. There is at least one planet that's known around a white dwarf star, and another one that is orbiting in a very tight orbit around a helium-burning star, which is a very surprising place to find one for reasons I can explain. You asked about habitability, and so that brings up that same issue that we don't really know what that means. Really, we don't know whether a planet is truly habitable if it has certain characteristics, or if that's just kind of projection from what we know here on the Earth. But that doesn't stop people from thinking about it and arguing about it and trying to make forecasts to help guide our future efforts. So there's a big argument going on right now, for example, about low mass stars. If you find a planet close to a star that's a red dwarf, only, 1/10 of the mass of the sun, and it's close enough to that star so that even though the star is hardly putting out any energy, the planet does have the right temperature for liquid water. Should we consider such a planet to be habitable? We really don't know. And there's a lot of arguments in the literature back and forth. On the one hand, if the temperature's right, water could be liquid, great. But on the other hand, if most of that energy from the star is at infrared wavelengths, could you really develop a kind of light harvesting organism that feasts on infrared rather than visible light? As you know, infrared light is a little bit harder on kind of general thermodynamic grounds to take advantage of. So that, and there's all kinds of other quibbles about the conditions that might exist around low mass stars. Are you familiar with this debate that goes on about red dwarfs?
I've heard some of this, and it'll bring us to discussion of the research done by Jill Tarter eventually in brown dwarfs and so forth. But yeah, very vaguely. So why don't you explain how that controversy plays out in your field for the benefit of the audience that might not be as familiar?
Like I said before, the great thing about red dwarfs, and astronomers know them as M dwarfs, but I like to just call them red dwarfs. They're red. They're cool relative to the sun. They are only 3,000 or 4,000 degrees Kelvin instead of 6,000 Kelvin. So that means that they're putting out most of their energy at the very reddest end of the spectrum and in the infrared. They're very low luminosity. They're hardly putting out any wattage compared to the sun. And they're small. And the smallness in particular is actually an advantage for a planet hunter. We haven't talked about how you find planets yet, but one of the most powerful ways we have is based on eclipses. That these stars are so far away that we cannot just snap a picture of the star and see the star and see the little planets going around it. That has worked in some cases, but it is not the main way that we get this information. The way that we get, we know of about 6,000 exoplanets so far. Maybe about 5,000 come from eclipses. Those very rare cases when a planet's orbit carries it directly in front of the star. And now we cannot see that happening as like watching a movie, but we can tell it's happening because the star appears to get slightly fainter. The planet's blocking some of the light that would usually reach us. So, for example, if we were watching the solar system from very far away and the Earth passed in front of the sun would appear to get fainter by about 0.01%. So a tiny amount, but potentially detectable. But if you make the star smaller, then a planet of a given size blocks a larger fraction of the starlight. So if you make the sun 10 times smaller, like one of these red dwarfs, then that means that the planet will actually block 100 times more light compared to that same planet around the sun. So a 0.01% signal suddenly becomes a 1% signal. And that's something that is actually quite straightforward to detect. The small sizes of these stars give them a lot of advantages if you're hunting for planets like the Earth.
Can you explain the challenges of doing photometry at that level?
If a star gets fainter by 10%, you can see that with your eyes. You don't need any special equipment. If a star gets fainter by 1%, okay, now you need a digital camera, you need a proper telescope, but you don't need a professional telescope. You can buy something out of the pages of the Sky and Telescope magazine that will allow you to measure brightness changes of 1%. If you want 0.01%, right, that's what you need in order to detect a planet as small as the Earth around a star like the sun. Okay, now you need a space telescope. You need to spend tens of millions, hundreds of millions of dollars to get a telescope above the Earth's atmosphere, which would otherwise corrupt our brightness measurements. And that's when you can detect such tiny variations in the brightness of a star.
So Josh, as you know on this podcast, we love to do what you're forbidden to do in polite society, which is to judge a book by its cover. But this book is not only little, it's also beautiful. It's full of color plates, hand-drawn, or not hand-drawn, but custom-made images, squashed Jupiters, all sorts of cool things. It even taught one of my kids Kepler's equal area law, which I'd struggled with for a very long time. Talk about the origin of the name of the book. Are you forced to name books in this way when you write for Princeton University Press? And then describe the cover illustration. And there is no subtitle, but what would you have used as a subtitle, perhaps?
This is part of a series that's published by Princeton University Press. There's a little book of black holes. There's a little book of cosmology. Now there's a little book of exoplanets. I didn't set out to write a book in this series, but I approached the editor there to say I wanted to write a book that tells the story of exoplanets, this field that is in so much progress, that is connected to the quest for life, but along the way has also revealed all kinds of other interesting surprises about planets around other stars. And what I want to be special about it, I want it to be very close to the evidence. I want to explain not just what we know, but how we obtain this knowledge and help the reader who really wants to know more about beyond the headline, about what we know now, what we can expect to know based on simple geometry, based on some physics they may or may not remember from high school, but to help them connect it all to see this as a scientific field. And so when I said that, the editor said, this will work really well in this series, these little books. They're kind of like briefings on a field of contemporary interest. And so it didn't turn out to be as little as some of the other books in the series. I think it's, 350 pages. But I do think, my main goal was it to be exactly that, to be a complete briefing for the non-specialist about where we are in this field, deeply grounded in the evidence itself.
Yes, it's truly wonderful, and the cover art is very sparse, but again, yes, it actually depicts a planet bigger than the stars, which is interesting.
That's right. We took a kind of minimalist approach to the cover, as you saw. You asked about a subtitle. What would be a good subtitle? Well, one of the themes that makes this subject so much fun to work in is the shifting boundary between science and science fiction. So maybe that would have worked as a subtitle. This field is funny in that the field as a scientific subdiscipline is pretty new, right? Only got going in the mid-1990s. But people have been thinking about exoplanets and speculating about them for centuries before that. And in the most recent period, that's been in the form of science fiction. So a lot of my favorite papers, a lot of my favorite projects involve planets that were known from science fiction. And, we're just kind of catching up with that. Planets that orbit around two stars at the same time. And it's like Tatooine from Star Wars.
Right, which makes an appearance in this book. As does the quote from Sir Arthur C. Clarke that any sufficiently advanced technology is indistinguishable from magic. And of course, I am the associate co-director of the Arthur C. Clarke Center for Human Imagination, which is how we got the name of the podcast, Into the Impossible, another quote from Sir Arthur. I want to play on that theme of technology, which plays out somewhat in the book, but not as much as it might otherwise be portrayed. So I want to ask is maybe it's not a simple question, but imagine what would it take for an alien telescope to spot Tokyo, the biggest city on Earth, from a distance of at least far enough that we haven't had a chance to really tell them about our existence, say more than 100 light years away or something, the 100 light years being about the time when the first radio waves were being broadcast hither and yon from the Earth. So how hard would it be to detect Tokyo from a distance of, 100 light years, for example?
So you're saying we want to see, not only do we want to see the Earth in an image, we want to see the Earth and its continents and oceans, and we also want to see a point of light coming from Tokyo.
Yeah, the pale blue dot.
No, that sounds pretty. That's that's not going to take. We cannot do that today. We will not be able to do that with the next space telescope being planned, nor the one after that. Okay, so the next space telescope. So right now we have the James Webb Space Telescope, fantastic instruments doing all kinds of wonderful things. There's already another one that's planned for launch. I think it's around 2027, the Roman Space Telescope. That one will likely be able to see planets that are the same mass as Jupiter as points of light in an image around some nearby star. So it'll detect giant planets, ones that are easier to detect than Earth-like planets. The one after that, and this is really, at the moment, it's not fair to call it a daydream, but it's just at the early stages of being planned, the Habitable Worlds Observatory. I hope it will be built in our lifetimes and launched, and that we'll get to enjoy it, but it's, going to be decades away. And its main goal is to just see an Earth-like planet as a point of light in an image next to a sun-like star. You're asking about, okay, now can we zoom in on that Earth-like planet and see evidence for civilizations on that planet? And my guess is that is, maybe a century beyond this Habitable Worlds Observatory.
What makes the Habitable Worlds Observatory unique? Does it have a sunshade? Does it have a fleet of telescopes the size of San Diego? What does it have exactly?
The thing that makes this so difficult is the contrast between the star and the planet. So if aliens are trying to find the Earth and they're looking towards the solar system with their telescopes, they have to contend with the fact that the sun is about 10 billion times brighter than the Earth, which is just reflecting the teensiest fraction of sunlight. So how do you build a telescope and a camera that can both detect a star and a planet in the same image, even though one is 10 billion times brighter than the other? What happens is the glare from the star causes light to spill all over the image. So what the Habitable Worlds Observatory will have is a very fancy version of a technology that already exists called a coronagraph. That is a telescope, but it includes some very, telescopes involve collecting the light with some giant mirror usually, and then concentrating it and bouncing it off various other mirrors before it hits a camera. And what's special about a coronagraph is that some very clever optical engineers have inserted some obstacles in the light path whose shapes are carefully designed so as to prevent the light from the star from ever reaching the camera, but allow the light from some nearby planet to get through. And so it takes a lot of precision engineering to get this just right. And this has been done for many years. In fact, the word coronagraph comes from the sun's corona, this hot outer layer of the sun's atmosphere that is very difficult to see unless you block out the light from the main part of the sun. So coronagraphs have been used in the study of the sun for many, many years. They have also been used to try to detect exoplanets with some success with the telescopes we have now, but not for planets as small as the Earth. That will require another few orders of magnitude of improvement in our coronagraphs. And that is what the main goal of the Habitable Worlds Observatory is to be able to do that. Beat those few orders of magnitude and detect the Earth as a pale blue dot.
Talk about how the various techniques compare. We talked about Doppler, occultation, transit methods. Compare and contrast them. If you only had one in your toolkit, what would you choose?
One of the fun things about working in this field is we do have so many different methods for detecting exoplanets. When you talk to the public, depending on who you talk to, if I say that I'm exploring exoplanets, they probably think we're out there visiting them, that we have rocket ships, that we're exploring the solar system and visiting different planets. Like, that's totally out of the question, right? All we can do is we're stuck here on the Earth. All we can do is use telescopes and cameras and our ingenuity to try to figure out whether planets do exist around nearby stars. So it's kind of amazing that there are 5 or 6 different ways that all work pretty well. The one that I work on the most, so my favorite, at least in the here and now, is the eclipse-based method, or as it's usually called, the transit method, where we wait for the planet to go in front of the star, and we can tell that's happening because the star gets a little fainter. We can get a spectrum of the star during those events, and we can learn about the planet's atmosphere and all kinds of other characteristics. So it's a very informative type of observation. The problem with transits is that transits are rare. It takes a special coincidence for the planet's orbit to be lined up just the right way so that it gets carried directly across the face of the star. Most planets don't transit. I keep coming back to this idea of aliens trying to find the Earth. But if aliens were viewing the solar system from all different directions, struggling to find the Earth, only 1 out of 200 of them would ever see the Earth transit. In most cases, the Earth never goes directly in front of the sun. So that is the heartbreaking thing about the transit method, is that you miss most of the planets. The method that came even earlier, and that has also been extremely productive, is the Doppler method. And that's one that's a big part of my research group as well. That's the one that's based on the fact that we always say the planets are going around the sun. The planets orbit the sun, which is not exactly correct, right? Really what's happening is that the planets and the sun, they're all going around the center of mass of the solar system, this point in space that represents the kind of mass-weighted average of all the bodies in the system. And that means the sun is moving, too, in response to the gravity from all the other planets. And that's what gives the Doppler method its power, because using the Doppler effect, we can tell when a star is moving, and specifically when it's accelerating, when it's moving around in response to the gravity of some planet in the system. So by making Doppler speed measurements of the star, we can deduce the existence of planets, and we can measure their masses and all kinds of other wonderful things. So that's another real workhorse of today's exoplanet scientist.
Another technique that's discussed, and I believe you call it the lazy method, which I'm very partial to, which is to let little chunks of material come on by. And this is very important to me because I give away these little meteorites, and I'll bring you one next time I'm by Jadwin Hall or wherever you're hanging out these days. And I will give you one, and I give them to all my listeners and audience members who have a .edu email address, and that's if you go to briankeating.com/edu. And if you don't have an edu email address, you can still try your luck, and I give out 1 or 2 a month at briankeating.com/list. That will get you into my mailing list where we talk about all sorts of cool stuff, and we'll be talking about this very interview, Josh, so I hope you'll become a member, and then I'll figure out a way to get you one of these as well. This came via, the U.S. Postal Service, and we'll get there. But gravity has brought other objects into our solar system that are fragments of extrasolar solar system. So talk about that method, and if it would be worth, instead of the generation that our great grandchildren will live to beyond the future Habitable Worlds Observatory, should it be worth spending a lot more money to go after these objects as they come through the Earth? I mean, they're not that rare and they're not that hard to catch up to. So talk about the lazy method and what that tells us about extrasolar planets.
Right. So, as you mentioned, the lazy method, if you want to call it that, is that let the exoplanets come to us. Right? We're too busy here to build big spaceships and travel elsewhere, and that takes too long. The little kernel of reality underlying this idea is that there have now been 2 detections of big chunks of material, objects that are more than 100 meters in size, flying through the solar system, that probably used to belong to somebody else's planetary system. They were probably asteroids or comets or something like that were ejected. Some kind of close encounter occurred in a different planetary system. That sometimes causes material to get ejected and never come back. So this material was just floating around in the galaxy for who knows how long, a billion years, before it happened by chance, to be directed towards our sun. And it came into the solar system. The sun's gravity deflected it in a different direction, but had no way of slowing it down or bringing it into an orbit around the sun. So the sun's gravity simply deflected it, and then they went off in a different direction, never to be seen again. So this has now happened twice. It's pretty recent. I think the first one, which went by the name of Oumuamua, was discovered maybe 7 or 8 years ago at this point. And then it wasn't long after that, but in 2 years, I think, a second one was detected called Borisov. And 2 is not very many, right? But nevertheless, this could be, and probably is, the birth of a whole nother field of astronomy, the study of these interstellar objects. Because even though there are only 2 of them that were found, the other thing that's important to know is that we hadn't been very good at looking for these objects for that long. We've only been kind of haphazardly searching for objects of this size and that are moving at these speeds. We haven't had the technology or the motivation to be scanning the whole sky on the lookout for these things. So just the fact that 2 of them were found after a kind of incomplete search implies that when we do get serious about this, we should find, could be as many as 5 to 10 per year. And we are about to get serious about it. There is a new observatory coming online. It was built for completely different reasons, called the Rubin Observatory. It's in northern Chile. And when it does come online, it will be especially good at finding these and all kinds of other objects in the solar system. So I expect that if they really are as common as they appear to be, based on the simple statistical calculations you can perform, based on the 2 that were discovered, if they really are that common, it is going to become a very big deal. We're going to see how often these things occur, how many times planetary systems eject asteroids and comets. We're going to measure their sizes and colors and spectra. We're going to see what they're made of. And we'll probably find some surprises. There have already been some surprises, as you might know.
Yeah, I've had Avi Loeb on the podcast many times, and of course he's quite convinced that this is not only from extrasolar planet, but it's extrasolar technology. And I wonder how you react to that. You seem skeptical in the book, at least, but has your opinion changed since the COVID years? And there's been other findings, including interstellar meteor.
First, let me try to explain the problem as I see it. So I mentioned there are these two of these interstellar objects were detected. One was called Oumuamua, one was called Borisov. Borisov appears to have been just like a comet. In fact, if you didn't know that it was moving at extremely high speed, if you just looked at it in an image and looked at its color and its shape and all of that, it would look just like a normal comet. So that was apparently a comet that was ejected from some other star system and ventured into our own by accident. Oumuamua is more puzzling. The puzzle of Oumuamua is that, first of all, it was smaller than Borisov. It was more... And in some ways, it looked like an asteroid rather than a comet. A comet is a big, dirty snowball, and it's the feature that makes it famous is when it gets close to a star, some of that ice sublimates, it vaporizes, and makes a big, glorious tail that you can see in an image, unmistakable. So Oumuamua didn't do that. So that suggests it was just a piece of rock, or rock and metal. It did not have any ices on it, and that makes it more like an asteroid. However, unlike an asteroid, it didn't just follow the kind of ballistic trajectory that one would expect of an asteroid going around the sun. Instead, it appeared to shift in position relative to its expected trajectory. Now, comets do that all the time. That's because when they do vaporize partially, that pushes off gas in one direction, and that pushes the rest of the body in the other direction. But asteroids, at least they're not supposed to do that. So why did Oumuamua deviate from its expected trajectory, even though, by all other observations, it appears to have been an inert asteroid rather than a comet? So I completely agree with Avi and many other planetary scientists who have studied this problem that there really is a problem here, that there is a puzzle of Oumuamua in that when we take the entirety of the data, we don't have a very compelling model that allows us to connect it all. There have been some proposals involving, for example, maybe it was a chunk of nitrogen ice, a big nitrogen iceberg. It has to be made of nitrogen for rather technical reasons that I won't get into just now, but, you know, and there are other ideas for what it might have been that would fit all of the data, but they're all kind of ad hoc. They're all just kind of made up to explain the data rather than being something we might have expected beforehand. Avi's hypothesis is also, in my view, like in the same category. It's kind of ad hoc that, well, maybe it is a piece of technology. Maybe it is a broken chunk of a spaceship, maybe a
garbage
kind of
barge,
sail.
Or a solar sail, right?
The great thing about Avi is that he's a brilliant physicist. His calculations are correct. It really could be made out of mylar or aluminum foil, and it would fit all of the data in a sense, you know. But is that hypothesis any better than it's a big nitrogen iceberg or, you know, or maybe just something we haven't thought of yet, something kind of complicated that mixes different, like part asteroid, part comet or something like that? So I regard it as a genuine scientific problem, but also a very frustrating one, because we only had about a month to study it before it got so far away that it's out of reach, even with our biggest telescopes. So it makes it, in my mind, kind of a sterile problem. There's a genuine problem. There's a conflict between theory and observation. It could be really interesting, but it's very hard to know how to make progress because it's gone. We cannot bring it back to the laboratory, you know. I mean, I suppose we could build a rocket ship and try to catch up with it.
That's what I told Avi, actually, in our first interview that we ever had in 2021 when the book first came out, and there was a whole splash on it. And I should say we're talking on the day after Lou Elizondo's book, Imminent, which details not only life in the universe, but terrestrial intelligence captured by the U.S. government and other agencies and witnessed by him and many other members of the military. But I told Avi, look, you're friends with this guy, Yuri Milner, and he's scheduled this $100 million project called Project Starshot to shoot cell phone-sized cameras to Proxima Centauri B. Why not, spend that money and catch up to Oumuamua? And he said, oh, no, we'll see many of these things with Rubin. And I said, that's true, but still, what if you don't? What if this is the only one? And you have to, leave the possibility that could actually occur. So I've actually said, yeah, you should save some money for actually going to these objects instead of just looking at them.
Yeah, I guess I agree that if it were our highest priority as a species to figure out what Oumuamua is, we could do it, right? We really could. But it probably makes more sense to wait a few years, see what Rubin shows. Maybe we'll see that Oumuamua is just one of a new category of objects that only really comes to light when we have a dozen of them and we can start to see what's going on. My guess is that is how it will play out. I can't be sure, obviously.
I want to jump to the nuts and bolts of what you do for a living. And, don't be afraid to be technical. My audience is the most brilliant in the known multiverse, in this area of the multiverse. That is to dive deep into what I think we scientists get paid to do, which is not to measure something, but to characterize how little we know about what we've measured. And, in other words, characterize our ignorance or uncertainty and ways that we could be biased into seeing something that's not really there. Talk about the different biases that tend to cause us to see certain exoplanets and not others. Talk about the nightmare scenario that keeps you up at night. If you were to see something, you conclude the book with a discovery in the newspaper of life and technology. How do you guard against irrational or maybe rational exuberance?
A lot of what I do has to do with the geometry of exoplanet systems. In the solar system, the geometric properties, when we're children, we learn that the planets all move in nearly circular orbits around the sun, that the orbits are all aligned with each other, so that it's like they're all grooves in the same record, which was an analogy that made sense, when I was a child, maybe not so much anymore. So I like to try to find planetary systems where those things are not true, where the planets are not moving on nearly circular orbits. Maybe they're highly elliptical orbits, or where the planets are spaced much more closely than they are in our solar system. That causes them to interact and have chaotic gravitational encounters with each other. Or to find systems where the planets' orbits are not aligned, where maybe they're, grossly misaligned. Another fun thing about the solar system is that planets are all revolving the same way, and the sun is rotating in that same direction. And we actually have a very good reason for that. We think that all of this rotation and revolution, all of that motion is inherited from the very conditions of formation of the solar system, from the gravitational collapse of a cloud of material that was swirling around. But it turns out that there are a lot of exoplanetary systems where that's not true, where you have a planet going this way, but the star is rotating in a tilted direction, or even a perpendicular direction. Or there are even some wonderful cases where the planet's revolving this way, but the star is rotating backwards. And so I love performing those measurements and trying to figure out, what are they telling us? Like, what did we miss in our theories for planet formation? What happened here, basically, that apparently did not happen in the solar system? Now, you mentioned bias in our methods, and that's something that also is a big preoccupation, not just of me, but everybody who works in this field, because we're in a field where the thing we're studying is extremely hard to study. Planets are so much smaller than the stars they orbit. They're very difficult to detect. And planets come in different sizes, some of which are very, very difficult, and some of which are merely difficult, right? So there's a range of difficulty levels. And so what that means is that the ones that we are successful in detecting are not necessarily representative of the planets that are actually out there. For example, my colleagues and I, we often study a type of planet called a hot Jupiter. Very exotic kind of planet. just as big and massive as Jupiter is in our solar system, but very unlike Jupiter in that its orbit is something like 100 times smaller than the actual orbit of Jupiter around the sun. That makes them very hot because they're so close to the central star. So hot Jupiters were this big shocking surprise when the first one was discovered in 1995. Some large fraction of all papers about exoplanets are about hot Jupiters. I would guess, 25%, just to make up a number. And a lot of the observations being conducted with the Hubble Space Telescope, with the Webb Space Telescope, they're about hot Jupiters. That's because they're so scientifically interesting, but it is also because they're very easy to detect compared to other types of planets. They're bigger. They don't take so long to go around the star. Both of those things make them much easier for us to detect than, say, an Earth-like planet around the same star. And so there's like a near obsessive level of detail in our knowledge, in our body of observations about hot Jupiters, even though they're not that common. If you pick a random star like the sun, there's only about 0.5% of a chance that it would have a hot Jupiter. And yet they're way overrepresented in our planet catalogs and in our scientific journals for that reason.
I did a lot of, diving into some of the surprising results. And you actually call them, you have these 3 different surprises ranging from misplaced giants, which hot Jupiters represent, high orbital eccentricities, which is also a big surprise to you. And I mean, all this is a surprise to me, Josh, because I'm an ignoramus about planets other than the one I live on. And then surprise number 3, that, planetary systems can be much more tilted and misaligned, right? Those are your 3 surprises. And then, when I look up, kind of the biases that we'll get into in a little bit more, the number 1 bias is that you're biased towards seeing, kind of close in and large objects because they go around much faster via Kepler's law. And they also can block more of the light because they're physically bigger. So does it worry you that the number 1 surprise thing is also the biggest source of potential, not confirmation bias, but measurement bias, sample bias? So how do you reconcile that?
It definitely is a big worry, and it makes it hard to draw the right conclusions from our data. When we survey, as we have in the past, say 10,000 stars and trying to find all the planets we can around those 10,000 stars, the planets that we find are so biased in their properties compared to the planets that surely exist around those stars. We only detect the giant planets. We only detect the close-in planets. So, for example, there's kind of a factoid that I hear a lot that exoplanet scientists have discovered that actually the solar system is the weird one, and that all of the exoplanetary systems have revealed that the Earth is very rare and unusual, and that the architecture of the solar system is quite extreme. I don't think that's actually true. I think, it might be, but we're not there yet. We cannot yet make that conclusion because we actually would have great difficulty detecting an exact copy of our solar system, even around a nearby star. Our methods don't work very well. The inner planets like Mercury and Venus, they're a little too small to be easily detectable by our methods. And the outer planets are simply too far from the sun for the transit method and the Doppler method, the real workhorses for today, for them to work very well. So what we do know is that something like maybe 1/3 of sun-like stars have detectable planets that make them kind of unlike the solar system, mostly in that they have a lot of close orbiting planets. But as for those other 2/3, we just don't know. They don't have any readily detectable planets, but they might all have systems that are very similar to the solar system. So it's still an open question, in my view, whether what we see here in the solar system is really unusual or not. And that's exactly because of the bias that's inherent in our detection methods.
The other thing that, kind of strikes me about this research is the kind of outsized influence of the Kepler satellite. It seems to have just, been the unlock, for you and your colleagues as, COBE was for mine, or WMAP. I can't resist a satellite named after my PhD grandfather, David Wilkinson, at your fine institution. Talk about the importance of that, and how many low-hanging fruit have been picked versus what might remain.
So Kepler really was in that same league as COBE and WMAP. I agree with that. It really opened our eyes to whole new categories of planets that we didn't know existed before. And it gave us our first glimpse at truly Earth-sized planets, which had not been detected before. And it gave us a lot of planets. It gave us thousands of exoplanets. Even to this day, most of the planets in our kind of official catalog of exoplanets come from the Kepler mission. There was something really frustrating, though, about the Kepler mission. And there's a reason why it didn't solve everything, which is that for partly historical, partly practical reasons, Kepler spent most of the time looking at a particular star field, happened to be in the Summer Triangle, and it stared there for 4 years straight. And so it found thousands of exoplanets that happened to lie in that direction in the galaxy. And in order to build up a big sample of stars, it had to look pretty far away, thousands of light years away in that direction, so that it had a lot of stars to base these conclusions on. What that means is that very often we found some weird, wild Kepler planet. First thing we want to do is obtain more data. We want to do spectroscopy. We want to take the light from the star, spread it into 100,000 colors, and analyze the intensity at each color in order to perform measurements of the mass of the planet and figure out what kind of star it's orbiting, all kinds of other reasons. And that usually ended in tears because the stars are too faint. Thousands of light years away, it's too far away. But that makes the star so faint that by the time you do divide up the light into 100,000 different colors, you hardly have any light to work with. So the Kepler stars were just too far away. So what we really want to do is something like the Kepler survey, but we want to explore the immediate neighborhood of the sun in all directions, not just the one direction where Kepler looked. And that is the mission of the successor to NASA's Kepler mission, which is called TESS. It's the Transiting Exoplanet Survey Satellite. It is up there right now. So the Kepler mission ended, I think it was around 2018, 2019, right around the time TESS was launched. So TESS is up there right now, scanning the sky every few years, looking for transiting planets, but it's looking for them around stars that are typically 30 or 50 times brighter than the typical Kepler star. So it's like suddenly having a telescope that's 30 or 50 times bigger. You get to learn so much more when the star hosting your planet is close by than when it is, thousands of light years away. So that's the fun right now, is that TESS is, we already learned a ton about what types of planets exist from the Kepler mission, and TESS is bringing them closer to us, allowing them to study them in greater detail with telescopes like the Webb telescope and large telescopes that exist at observatories all over the world.
Yeah, I was curious about Webb and how it's impacted your research in particular, especially since, getting time on it is like, winning the lottery, twice in a row. How is it impacting your research? And
yeah, what's not as bad as that? Like to get time on the Webb telescope, I think the odds are about 1 in 10. If you have some good ideas, if you keep at it, you'll get your Webb time. So Webb is most famous for spectroscopy, this technique of dicing up light according to wavelength or color, and learning about the composition of objects and all kinds of other physical properties by studying those spectra. And so Webb is spending a lot of time, I would guess 15, 20%, all the observing time on Webb is being spent looking at the atmospheres of exoplanets, using these tricks related to transits, that when a planet goes directly in front of the star, some of the starlight filters through the planet's upper atmosphere, which is partially transparent. And so the molecules in the planet's atmosphere absorb their favorite wavelengths as the starlight passes through it. And we can see that in a spectrum with the Webb telescope, at least in some cases. So there's a lot of work going on now, not only to know that an exoplanet exists and to measure its size and its mass, but to see which molecules are in its atmosphere and what the local conditions are, what is the pressure, what is the temperature, and things like that. In addition, so that's actually not what I do personally. I am a fan of that work, but it is not my own kind of first-person research. I'm not much of an atmospheric scientist. What really excites me about Webb, in addition to that, is that it's just a big telescope, much bigger than the Hubble telescope, and it's in space, so we get very, very precise measurements. And so we might be able to see things that we just couldn't quite see with Hubble or any previous telescope. For example, one thing I'm working on actually at the moment with a graduate student here at Princeton. One of the cool things about Saturn, if you look at a picture of Saturn, you see the rings, obviously. That's just dazzling. But then after you get over that, you look at the planet itself, you see it's not a circle. It's actually squashed a little bit. That's because it's rotating pretty fast. I think it takes like 9 hours to go around. And that causes it to be distorted from a sphere into an oblate spheroid, a squashed sphere. Wouldn't it be cool if we could see that same shape change for an exoplanet and get a fix on how quickly it's rotating? So with Webb, we might be able to do that. Again, relies on this trick of transits. These planets are so far away, we can't see them even as a point of light in an image. So we have no hope of actually seeing a silhouette like that. But when the planet goes in front of the star, it blocks some of the light, and we see the brightness of the star goes down. The signal looks slightly different if the planet is a sphere compared to if the planet is a squashed sphere. So especially if that squashed sphere is tilted, like Saturn is tilted 20 degrees or something like that. So with Webb, we actually have a chance at being able to measure the shape of an exoplanet that's induced by its own rapid rotation. Hasn't happened yet, and in fact, this project I'm working on with this graduate student is a null result. We did not detect it. But we're not so far, I think, from being able to do it, and Webb is just getting going. And furthermore, there's a host of other things that might pop out by applying Webb just as a very, very precise photometer, as a device for measuring brightness variations of stars. For example, if planets have big rings like Saturn does, and if those rings are opaque, we might be able to use the same trick to see them. If a planet has moons, then maybe we'll see the transits of those moons as they go ahead of the planet or behind the planet as both of them cross in front. There's a group at Columbia led by David Keating, and he has, I believe, an approved program with Webb to go looking for moons and this rotational effect and other effects for one of the best possible targets that's currently known. So it could be that within months, maybe as long as years, we'll be able to see some of these really subtle things thanks to the ultra-high precision of Webb.
As we wrap up, I want to get your impression of why a young person might be attracted to this field. We have a lot of high school science enthusiasts all the way up through, Nobel Prize winners that listen to this podcast. But what is so appealing about this field that you've chosen to dedicate not only this phenomenal new or a year-old book now, but really just a breeze to read. I listened to the audiobook. You narrated it. It was lovely. Why should a young person be interested in this field, and what are some of the perks of being a member of it?
When you're thinking about what field to get into as a young person, it is not necessarily the best idea to ask senior people. And I have sort of regrettably become a senior person myself. You want to trust your own instincts. You want to see. You want to learn as much as you can. You want to eavesdrop on conversations that are happening in various scientific fields and get a sense for yourself, like, where is the excitement? Where are things changing the fastest? Where might I be able to make a contribution? That's a much better strategy than just kind of asking around. I mean, that might give you some leads, but you should never trust senior people completely because we freeze out, we get comfortable and we're not paying attention necessarily to what are really the next hot upcoming fields. The second part of your question, which is maybe more direct answer, is what is about exoplanets that's exciting? I was in this situation. So when I was in the midst, when did I make this change? I guess it was when I was a postdoc. I was working in cosmology. Basically, I was working in a very similar field that you work in. I was working on gravitational lensing. I was trying to find lensed quasars and use them to measure the Hubble constant and this trick that I'm sure you're familiar with. And the senior people I was working with seemed to think I was making good progress. And I would go to conferences and I would give my talk and, things seemed okay. But I got a sense the field was stuck. At least the subfield I was in was stuck. Certainly I felt stuck. And when I went to the conference the next year, like my talk wasn't that different and neither was anybody else's. I felt like nothing much was happening. And yet at the same time, the first few exoplanets had been discovered. I think the first transiting exoplanet had just been discovered. And there was just so much excitement. And I was in a place where there were a lot of people who were interested in this area. And I could tell that from one year to the next, the talks were all totally different. It was a completely different feeling. So the sense of being part of something that had just begun, but was clearly going to be very big, that made a big impression on me and convinced me myself that it was time to switch. This was a time of opportunity. The field is still growing. There is a lot of life left in the field of exoplanets. It is not an old, mature, field just for senior people. Far from it. It doesn't have that same kind of exponential growth that I felt at the beginning of the field. Naturally, fields kind of have their own kind of trajectories. It's a little more sedate now, but it's still growing. But what's great about it is that, first of all, the barriers to entry, I think, are quite low compared to some other fields, like cosmology, for example. To get to the frontier in cosmology is quite difficult compared to what it takes to get to the frontier in exoplanets. Not only in terms of knowledge, you have to learn general relativity and perturbation theory, and maybe you have to learn some new technology, and you have to be part of a big 1,000-person collaboration. There's a lot that's involved. Whereas in exoplanets, you need to know classical mechanics, you need to know about orbits, obviously you can go a lot deeper than that, but you can start making progress from a much smaller knowledge base. And there's a lot of public data sets that are out there that allow small groups to make interesting contributions. So that's another thing I still like about this field, is that the barriers to entry for new people are pretty low. It's all technology driven, and technology is getting better and better. So that helps to set our agenda. We can foresee technological advances, and we know that whenever we can figure out how to measure starlight better than we have before, we're going to find more interesting exoplanets. History has prepared us in that way.
Josh, you can tell from the neon glowing sign behind me, I'm a fan of science fiction, especially Arthur C. Clarke, who gave us the name of the podcast, after all. I'm not sure you are that familiar with that particular.
I am a big fan, but I don't recognize the quote.
So 2001: A Space Odyssey. Dave wants to get into the pod bay, and he says, "Open the pod bay doors to Hal," and Hal refuses to open the pod bay doors, leading to great hijinks at the end of the film. But the pod was the motivation for an engineer working at Apple for the name iPod, and then that as a storage protective unit that you couldn't get into, I guess. And then that led them to create the concept of the podcast, which is what we're doing right now. And as a fan of science fiction, you might also recognize Sir Arthur's famous Rendezvous with Rama, which has to do with a spacecraft which is initially thought to be an asteroid, like this little chunk that you'll get at briankeating.com, or a comet, and the crew is encountering it and learning about it, and throughout the series. At one point, they say something very fitting, which I think is perfectly apt for our conversation. They said, "The more we learned about Rama, the more we realized how little we knew about the universe." And Josh, I want to thank you for illuminating a great deal of excitement in your field and in astrophysics in general, and being so generous with your time. Thank you so much.